This video is about series and parallel resistances. It corresponds to section 4.5 of the Applied Analog Electronics textbook. Alright, there are lots of different ways to connect resistors, but there's two very common ways. The perhaps simplest one is series connection, where each resistor is connected sort of head to tail with the previous one. Incidentally, this zigzag symbol here is the symbol for a resistor. So here we've got three resistors. Let's call them R1, R2, and R3. And I say we're calling the resistors R1, R2, and R3. We'll also use the symbols R1, R2, and R3 for the values of the resistance, so how many ohms they are. Let's give some names to the nodes. Okay, so we've named the nodes A, B, C, and D. Now, what does Ohm's law tell us about what's going on here? Well, the voltage across resistor 1, that's VAB, is equal to R1 times the current from A to B. And similarly, VBC is the resistance R2 times the current from B to C. And finally, VCD is R3 times the current from C to D. Alright, that's very simple. It doesn't really do much for us. We've got three variables, three equations here in 6 variables, 9 variables. Not really much you can do with that, except we have a special property here because these things are connected in series and there's nothing else connected to node B, nothing else connected to node C. So any current that goes through R1 has also got to go through R2. And that same current has also got to go through R3. So what we have is that all three of those currents are the same. Let's just call it I. So we have it, this is R1 times I, this is R2 times I, and this is R3 times I. What happens if we add these three equations together? Then we would have VAB plus VBC plus VCD is, well, R1 plus R2 plus R3 times I. Okay? Let's look a little bit more carefully about what happens when we add these voltages together. Remember that voltage from A to B can also be represented as the voltage at A minus the voltage at B, comparing them both to some arbitrary node that's ground. And VBC, well, that'd be VB minus VC, and VCD, that'd be VC minus VD. And that's again equal to the R1 plus R2 plus R3 times I. But we've got some stuff here that cancels. Minus VB and plus VB, minus VBC and plus VC, cancels. And we ended up with just one thing, the voltage from A to D is equal to R1 plus R2 plus R3 times I. Well, voltage from A to D, that's the voltage across the entire chain here. I is the current through the chain. So what this is saying is that resistors in series add. And that's a very nice, simple rule that's worth remembering. When you've got resistors in series, you've got no connections to stuff in between them, they're just in series, the whole chain has a resistance that's equivalent of just adding the individual resistors. Okay, I said that was a simple case. Let's look at a slightly more complicated case. Another common way of connecting resistors is in parallel. And so we'll end up with let's do again 3 resistors, R1, R2, R3. We've only got 2 nodes here, but each of these resistors might have a different current. So we'll have I1 through that resistor, I2 through the second resistor, I3 through the third resistor. What does Ohm's law tell us? Well, let's write it this time in terms of the currents instead of the voltages. We have I1 is voltage AB divided by R1. I2 is voltage AB, only got 1 voltage, divided by R2, and I3 equals voltage AB divided by R3. We can again add, and we get that I1 plus I2 plus I3 is VAB times 1 over R1 plus 1 over R2 plus 1 over R3. Now, what is I1 plus I2 plus I3? Why are we adding those currents? Well, these currents are all in parallel. If you think in terms of the hydraulic analogy where we had a bunch of pipes in parallel, the flow through each one adds to the flows through the parallel ones. So the total flow from A to B is the sum of the flows through each of the different branches it can go through. But this now is back in the form of Ohm's law. And what we end up with is that the resistance, which is VAB divided by IAB, is going to be 1 over R1 plus 1 over R2 plus 1 over R3. And that is the basic formula for resistors in parallel. It's a little messier than the one for resistors in series, but there's a nice way to think about it that makes it just as simple. If we think of conductance instead of resistance, conductance is just 1 over resistance. So what we have here is that conductances add in parallel. So we add up the conductances, we ended up with a new conductance, and inverting that to get a resistance gives us the standard formula. So what we have, 2 very simple formulas. Resistors add in series. Resistance in series adds, conductance adds in parallel. And from that you get 2 formulas, R1 plus R2 plus R3 for series, and 1 over R1 plus 1 over R2 plus 1 over R3 in parallel. Those 2 formulas are important enough to be worth memorizing. There's very little memorization in this work, very little memorization work in this class, but those 2 formulas are worth the effort because you will be using them over and over and over again.